Afternoon, everyone. We're just going to do a small stream today, a little Mercury Atlas tutorial. We can see we've loaded up into a cold and dark configuration. And everything is looking pretty good here. So to start out with, we'll turn the cabin lights on to both. And we'll get our checklist going. Right now we are on ground support equipment power. The first checklist you're going to run is the T-minus 90 minute. And we can see, first things we need to do are the main batteries. They need to come in. So we'll come over here and we'll get our main batteries in. Our isolated battery needs to come on and our 2 standby needs to come on. So of course, on the Mercury, there are 3 main batteries. Main battery 1, 2, and 3. There is a bus dedicated for backup power supplied by 2 standby batteries, and a bus dedicated to the sequencing and staging of the rocket, titled the isolated battery. Next up, we need to turn on all of the fuses for the spacecraft. Yes, hello. Yes, this is just a short stream for today. Just helping out Old Man Rebel with operating the Mercury. Okay, all our fuses are on the number 1 position. Squibs off. Next, auto retro jet switch, arm. ASCS, normal, auto, gyro normal. Control handles need to be in. Retro delay needs to be instantaneous. Photo lights on. Cabin lights both. Telemetry low frequency on. Rescue in auto. Launch control off. And all rings need to be seated in their in and guarded position. This is default, so we're good on all of those. Control fuel, both 100% on the auto tank, 100% on the manual tank. Rate of descent should be 0 feet per second. Barometric altimeter should show 0 feet altitude. Satellite clock should be synchronized. Looks good. Cabin pressure, cabin air, sensor temperature, steam vent temperature, suit environment, cabin O2. Our oxygen quantities, primary and secondary, need to be 100%. Our DC volts, all of these need to have volts. Right now, they should show no amps because the batteries currently are not powering. We're not on internal power. We're currently on external. Yeah, I seen him do retro in the Mercury on a reentry orientation, so I'm just gonna teach how to do the Mercury stuff. So that when he does his videos, that they can be more in sync with the timing of the audio for the missions, because of course if you retro at the wrong attitudes, your audio is going to be completely unsynchronized after that, and there'll be no hope for synchronizing it. So our cabin fan and suit fan switches need to be normal, and this is going to help control the temperature in the cabin. We'll see that temperature start to change. DC volts knob needs to be on main, yes. Ammeter needs to be off for now. The auto stabilization control system AC bus, alternating current bus. This is the power of the system for the autopilot. That goes to norm. And we need to take our standby battery on, and our isolated battery needs to be transferred to the standby bus. Now we can see our main bus has a lot of potential because we have all of our backup systems running on it. You can see here has the same amount of volts, but the standby, right, because we're not using the batteries, they're just on the bus, they're not putting out any amps, we have so much potential energy in the form of volts. It's good. Inlet valve power on. In bypass, we get essentially cut off, so we want this to be on normal. Audio bus normal. Our AC voltmeter needs to read 115 volts on the fans. We've got our standby AC bus, our ASCS AC bus, our 150 volt AC bus, and our 250 volt AC bus. Here, fans measures the main power. Main power for the spacecraft goes through the fans bus. So that's very important. Vox, voice-operated transmission, that's this switch here, turns to power off. UHF DF on norm, this is for landing. UHF select, high power. Transmit off. Beacon, ground command. All audio warning tone switches to tone. Good. Warning lights can be bright or dim, user preference. Emergency O2 handle should remain in, like this. If it's out, you get O2 emergency, so make sure it's in. And now your environmental cooler, your suit temp to mark, cabin temp to mark, and inverter, the AC inverter cooling to the mark. This would be 3 for all of them. And now you need the maneuver switch turned on. This maneuver switch, never touch it after this. This is responsible for the gyro spin up. So the spacecraft attitude is measured by torque caused by spinning gyros. If you turn the switch off, the gyros will spin down. Here you can do a light test. As you can see, it's sometimes very bright for the green. You switch it to dim, you can see the green better. Sometimes that means that the other ones become very bright and unreadable, so you can switch it back to bright. This is something that I might talk to Petrie about, making just a small graphical modification to that. And now we'll come down to T-minus 40 minutes. So here, time to launch, we'll bring it down to T-minus 40. minutes. Now we can run the abort capability test. So ammeter needs to be turned on. Again, no volts or amps, no amps because we are not running on batteries, so we're all volts. Capsule squib needs to be armed. And now we need to select the isolated battery on the knob. This is the battery that controls the staging of the rocket and the firing of the pyrotechnics. Now from here, we can request abort capability test. We can see a rise in our amps as the isolated battery is being used to power the light and arm the escape system, and we see a fall in the amps. This is good. That means that our squibs will work just fine. The rocket can stage, the abort tower can work, the abort light will work, everything that is not on the main bus and is everything to do with the criticality of the mission is on that battery. So this check is absolutely critical to the system. From there, you can begin your T-minus 20-minute abbreviated interior check. This will switch over the retro delays and stuff, and we have it on instantaneous right now, I believe, in case of pad abort. That's why that switch is there. So it's something that gets fixed later on, so you never want that to be on instantaneous because the retro sequence factors for a normal delay. Instant delay is only for emergencies. So we're at our T-minus 20-minute mark. Again, verify all switch fuses are in the number 1 position. Number 2 is still powered, but it's the backup fuse. When they blow, it'll automatically go like that. So if you ever see a circuit breaker blown, bam, power to the next position. Squib and auto retrojet are armed. All of this should be to the left. Again, retro delay, back to normal. Rescue switch in auto. Pressure regulator, we don't want water sealed, so it needs to be in. All of these need to be in on auto and covered. We make note of our fuels, accelerometer, ROD, barometric altimeter, our environmental readings, and they're all looking really good right now. We can take this back to main, verify fans are on normal, ASCS is on normal. These need to be on and standby for the time being. Fans AC bus switch needs to be normal. You could move to the standby bus, but all normal is good. Got your Vox power as off. UHF-DF still normal. High power transmit off. The beacon for the transponder needs to go to continuous now. Emergency O2 handle still in. And now at T-minus 10 minutes, we'll run our full internal power. So let's bring it down to 10 minutes. Here at 10 minutes, let's go full internal power. We'll talk to the blockhouse. We'll say switch to internal power. Now look at that. We've got amps and our volts comes down on the batteries as our amps go up. And all things have the amp spikes now. So we can see all battery conditions are good. Now we'll take the isolated off of the standby bus. So it's not feeding onto the standby bus, which is feeding onto the main bus. So it's isolated now completely. Standby batteries, they can be isolated now. And now we are just running on the main batteries. And our main bus shows good amps and volts. Now we'll come down to the final checks, T-minus 5 minutes. So we'll bring it down to 5 minutes. And that flashing is a small graphical glitch. Here we'll go outside just to sort of calm that down. There we go. Now launch control to ready. Verify all to mark. Transmit on ultra high frequency. You can perform the radio check if you would like. You can see, good radio check. Remove the time 0 switch, but do not press. Monitor battery 1. Now this is important. The reason we want to monitor specifically battery 1 is because if we're monitoring the main bus and a battery goes out, we won't see the main bus be reconfigured. When we're monitoring any of the batteries, 1, 2, or 3, the checklist just says 1. If we lose battery 1, we see a dropout on the volts and the amps. If we lose battery 2 or 3 while monitoring battery 1, we'll see a sharp rise in the battery amps. So by monitoring any single battery, we're able to tell the condition of the other 2 batteries. So this is why we monitor a specific battery instead of the main bus, because the main bus, unless you lose all 3 batteries, will never fluctuate. Only the batteries will, to keep up. And our squib and our auto retrojet are armed. From here, at the T-minus 30-second, we can begin our ascent check. Here we can see monitor for the abort light, monitor the isolated battery voltage, monitor the cabin pressure, monitor all the DC volts and amps and the AC volts. On booster SEP, if we're in the Atlas, we run the BECO checklist. So let's get down to it.
Nine, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Umbilical disconnect.
Loud and clear. Roger, we're programming and roll okay. A little bumpy along about here.
So we did get our roll program in.
Stand by for 20 seconds. Roger. 2, 1, mark.
Now we can see our pitch program is in. This purple needle has deflected and the pitch is coming down now. We can follow all of that on the gyros. Also monitoring, we need to make sure that the cabin pressure is being relieved by the cabin pressure relief valves as we ascend. Once we get to 5.5 psi, the cabin valves should automatically close. This is to maintain structural integrity of the cabin, as structural integrity is derived by a 5 psi plus differential pressure from the inside and the outside. So as we ascend and the pressure falls, we need to make sure that that 5 psi differential maintains, or we'll lose structural integrity and have a collapse of the spacecraft. Let's monitor our isolated battery voltage. We can see it's good. And the rest of our DC systems are good. Cabin pressure locks in at 5.5. And the cabin valves are now remaining sealed. Good. Our AC volts are good. Of course, the standby bus will show no voltage as it's not activated. But when we switch to standby, we can see it. Preparing for BECO now, we'll see a rise in the isolated volt as the stage below us gets ditched. Once you see stars, you know that you are ready for BECO. So let's run the BECO checklist. Jet tower will process in amber, and after 20 seconds will turn green. We can see isolated spike, and it will happen again when the tower is jettisoned. We can see jet tower command is processing. Jettison tower is green. Now we can run the BECO checklist. Here, auto retrojet switch off. Retrojet fuse off. Emergency retrojet fuse off. And now, as you can see, we're aimed at the horizon. Here, the sustainer of the missile activates what's called terminal guidance phase, or guidance convergence, depending on which rocket and what time. I've seen SpaceX uses terminal guidance, NASA tends to use converged guidance. But this essentially just means that the rocket will be pitching up and down. And the reason it does this is we're tracking. We need to make sure our apogee is controlled and our perigee rises. So we pitch up and down. When we pitch up, we put more energy into the apogee, and when we pitch down, we subtract energy from the apogee and put it into the perigee. And this is what the system is doing. Here we can see our attitude data as well. But that's not important because we get the needles here. We can see we're getting real shaky, so we are starting to approach cutoff. Now keep in mind that perigee will not begin to rise until just before cutoff. The altitude of this rocket is really slow, so when you start seeing this number rise, you're going to have cutoff in probably 2 or 3 seconds, maybe less. We are approaching orbital velocity. We can see our apogee and our perigee and our inclination on this map as well. We'll just run a check on our batteries. All batteries are looking good. Seco.
Posigrade's fired, okay.
We can see that spike as the posigrades fire. That's good. We are now separated, and we can see the automatic turnaround. Touching nothing, this is retrograde attitude for the rocket. Whatever it brings you in on, this is 100% the retrograde attitude. This is what it should look like. If you're pointing up, you're going to increase your apogee. You'll still decrease your perigee if you're in retro attitude. You'll get atmospheric interface, maybe. Most likely you will because of the short orbit. You run the risk of stranding yourself. But if you were to re-enter in entry attitude, you would actually increase the heat flux with the spacecraft. You would end up disintegrating because you'd run through your ablator. You'd spend too much time in the atmosphere, increasing the overall heat flux. Even though the temperatures are lower, the heat flux is still higher and you burn up. So this is entirely an important orientation. With gyro norm, 0, 0, 0. Right? Now we'll run our in-orbit checklists. So we'll add a stream marker there. And let's run those orbit checks. Checklists, orbit. DC volts, we need to monitor the main bus now. Landing bag switch off. Retro delay still normal. Emergency retro sequence off. Emergency drogue deploy off. All instruments check. We can go back to low transmission on UHF, and when out of range, switch to high. Entirely up to you, as the radios don't exactly consume much more power. You can also do just HF for even lower consumption. You can see how this affects our main bus. all systems affect the main bus. So we've completed our orbit checklist. Let's go over a few simple things, right? If for whatever reason you were to lose your main buses, you'll experience this. You can power them up by activating your standby batteries. Your standby batteries will now power the main systems, like so. If for whatever reason you lose your standby batteries, you can also power with the isolated battery. But you never want to do this unless absolutely necessary, because remember, that isolated battery is responsible for getting you home. That isolated battery is responsible for getting you home, so you never want to do that unless absolutely necessary. You'll also notice when the fans are off, eventually we get an excess of suit H2O and cabin H2O. This is completely normal. The fans act as a dehumidifier, so it's important that they maintain on. When you turn, what is it, ASCS? No, it's one of these. Cabin fan. One of these buses also made these two lights come on. That's important to note. I don't remember exactly which one. I'll have to figure it out later, but... Ah, right. It might be... Was it the programmer? Nope. Was it... One of these will make these lights turn on fictitiously. So that's something to keep in mind as well. If you lose that bus, these lights will be doing very strange and unusual things. So now you can see, as we're drifting, we're using a lot of fuel, right? Let's activate manual control of the spacecraft. Aux on, rate command, manual handle out. Now we have complete control. But let's say we didn't want that, right? We'll go back to auto. Let's say we want to just have auto control pitch or roll and yaw. Let's only control pitch. We can pull the white handle, pull the manual handle. Now we have control of pitch. The spacecraft still controls the yaw and the roll, but we can pitch around to whatever orientation we want. You can do these on any axes. When you put it in, the spacecraft will automatically realign. Good. So, fly-by-wire is another system. You can gain manual control, but keep in mind, fly-by-wire uses significantly more powerful jets and burns the auto tank. So if you want to only burn on the manual tank to save your auto fuel, this is the configuration you're definitely going to want. Now we can control our attitude however which way we want. If you take a look, this tells us our orientation. The square tells us the speed of the spacecraft, right? So here is perfectly still, almost as good as you can in space. We can see this is our rate of pitching up. 1, 2, 3, 4, 5, 6, 7 degrees almost every second. There's 7. 6, 5, 4, 3, 2, 1, 0. You can do it down, and the same applies to all of these. So if you're ever spinning out of control, look at this. You just bring it in, bring one in, bring the other in, and now bring the last one in. It is very simple to regain control of the Mercury. Keep in mind that you can't do it from out here. Outside, in space, there is no reference for attitude and there's no reference for speed. We can go crazy with this and we can try to regain control. We can say, wow, Here's a lot of roll. Let's calm down the roll. Look at that. Oh, we're adding to it. So let's go the other way. Now which way are we going? It still looks a little bit like roll, but here is some pitch. Which way is it? We don't know, right? This is why our instruments are extremely important. External view is great when there is nothing to do, but external view doesn't cut it when you're supposed to be flying. Maneuvering to retro attitude in manual is as simple as getting roll to 0, and then pitch to 0, and now yaw to 0. As you can see, when you yaw, you may slightly affect the other needles, so you may need to make some minor corrections after your yaw is finished. And again, the rate stabilization control system indicator, the RSCS indicator, the rate indicator, helps us perfectly gain control of the spacecraft, even with manual control and no damping. Here's retro attitude again. A really nifty trick for retro attitude is take a look at the Earth. The edges surround the box. This is another quick way to tell retro attitude. Is there any other questions before we get along to finishing up here for the reentry? Any other questions about how to yes, actually there's one thing I didn't cover. Gyros free, right? So gyros free, it represents an orientation from an attitude. So here, let's say we wanted to hold this amount of pitch, right? We wanted to hold this specific attitude. Gyros to free, gyros to cage. Now back to gyros to free. Now check this out. As we maneuver, we sort of get an attitude from the orientation we had before, right? So when we bring these needles back to 0 on gyros free after we use cage, we can enter the same attitude we had when we caged the gyros. We can see we're seeing the same stars in the same position, all at 0. This is what gyro free does. We can see we can lock on to this horizon in this exact attitude. Cage. Now when we maneuver up, here we can see we're a little bit off in pitch, and when we bring it back to 0, now there's the exact spot. So that's what gyro free does. Gyro norm reorients the gyros back to showing your retrograde attitude, and you can maneuver to this point. Now we've got lots of time to retrograde, so we'll time skip. For the purposes of this tutorial, we'll time skip. So here we are, 30 seconds down to retro time. We come to our checklists. We come down to entry. Look at this. TR minus 30. Time to retro minus 30. Approximately 30 minutes before retro, we need to make everything really cold. Now it says approximately 15 minutes before retro. And you can see when it's getting colder, we do get a little bit excess H2O. Completely normal. Here we are, 15 minutes to retro. Let's get our retro sequence fuse on. Verify retro rockets are on. Verify the rest of these fuses are on. We already know they're on since we didn't turn them off. Squibs need to be armed. Auto retrojet remains off. Telemetry low, on. And now if we're on HF, we switch to UHF at this time. Beacon switch remains continuous. Retrojet fuse off, retro manual fuse on, which it is. Good. Attitude select retro. Now let's go to auto. You want to do this roughly 5 or so degrees from your retro attitude, but we do have enough fuel to spare for this. And we're in retro attitude. Now we can start retro checklist. So we'll come down. When we get to 5 minutes down to retro, the 5 minutes to retro telelight will come on. This officially begins the clock's timing of the retro sequence. This is like the Soyuz retro 1 indication. And now when we come down, 4, 3, notice the Earth horizons still touch the box, and the landmarks still drift straight up like this. Good. We're still 0, 0, 0. When the retro sequence starts at T-minus 0, so here we go, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Retro sequence start. When we're in the retro attitude, this light will also turn green. Now, there is a normal amount of time. The retro sequence is processing, it's measuring our attitude, and now it's preparing to fire the retro rockets. We get the retro warn light on for about 10 seconds. And once that turns off, the fire retro turns orange and ignition. We can see the retro attitude light may turn orange. The ASCS will keep it in pretty good. Fire retro is now green, and we have cutoff. Once that's done, we can start the re-entry checklist. Auto retrojet switch arm, retrojet on, emergency retrojet on. After 60 seconds, the jettison retro telelight goes green after receiving the fire retro signal. So we come across for a minute, and we can see jet retro is green. Now, what we do is, look at this, attitude select re-entry. All we do is flip this switch, and the ASCS, after a couple seconds of processing, will automatically know which attitude we need to maintain for entry. It brings us up. And like in my tutorial video, somewhere between this mark and this mark, we'll have our perfect attitude capture. When we hit entry interface, the retract scope telelight will go green and the 0.05G telelight will go orange. We'll then notice a 10 degrees per second roll rate. So let's bring us down. Nice and slow. We can see we're holding a near perfect attitude. We don't want to come down flat into the atmosphere or we'll die, right? We need to come down sort of at this nice, gentle angle you see here. Our rate of descent is picking up. That's good. We can see retract scope, 0.05G. We can see the atmospheric forces are having their effect, and we get that roll rate in. So now we have no control of the spacecraft except for in roll. And the ASCS will automatically roll to maintain control. Sometimes it can glitch out like this, but if you just leave it, it will fix itself. Yeah. At this point, if you really wanted to, you can relinquish control of the ASCS because it's not needed anymore. The aerodynamic forces will keep us 100% stable from here on out. But you can also leave it on if you want. We get our entry, and we can see we're perfect right down the middle of the flame. Now we can start our landing checklist. Here, emergency drogue fuse needs to be on, but before 30,000 feet, right? So once we register radar altimeter, then we turn it on. Until we register on the until we register on the barometric altimeter, we do not turn this fuse on. Accidental deployment of the drogue chute will kill us. We can see ASCS is keeping it perfect right on the money. And look at how much fuel we saved. We were even doing all the maneuvering for the tutorial. Look at how much fuel we saved just by running automatic on the entry and manual for the rest of the mission. All right, auto fuel should only be used for entry. All that fuel saved. It's really good. You can see as we're coming down, we need to maintain structural integrity of the spacecraft. So the cabin relief valves are going to open in the other direction, and we're going to pressurize the cabin as we fall. We always want a delta pressure of 5 psi to maintain structural integrity right until we open that hatch. But as we fall, the pressure will continue to rise, and we'll need to relieve that pressure. Yes. So as we're coming down, you'll see this coming up, and then eventually you'll see it stabilize with atmospheric conditions as opposed to 5 psi over. And that all happens automatically with the cabin valves. Yeah, noticing more graphical glitches lately, wondering what's causing that in the code. I have no idea. I think it's something with the post-processing, if I'm going to be completely honest. I've been wondering that myself. And I got to report some of these things, especially this. Like, this text is just way too hard to read. This is good, except when you get the orange, now that text is just way too hard to read, so you need to go bright, right? So they need to switch this around, right? This is just way too much for it. It just needs to come down a little bit, because it's really hard to read unless you zoomed all the way in. Oh, we can see we're breaking the atmosphere now, lower parts of the atmosphere. Eventually, the roll will stop. ASCS will cause the roll to stop. And we're down. We're on altimeter now. Before 30,000, that needs to come on. But we are on the barometric altimeter. Look at this. At 21,000 feet, we get the drogue deployment. And at 20,000 feet, we do the snorkel. Yeah, the lights is just it's better in Gemini. In Mercury, it's just really bad for whatever reason. Actually, I think Mercury might be my favorite of the reentry spacecraft in terms of how reentry does it. Just because this is just nice. I mean, it's like being in an old-timey submarine. Snorkel, emergency O2, and act that alarm. Landing bag switch goes to auto before the main deploy is out. And now we wait for the main light. But yeah, Gemini is overall my favorite, but Mercury is my favorite implementation of the reentry spacecraft. The main is out, so UHFDF can go to real time. This is UHF delay function, and now we switch it to real time instead of delay time. We water seal the pressure regulator, and now we wait for impact. Orbiter does not have a more hardcore equivalent. To be honest, reentry's implementation of Mercury is probably the most accurate I have seen. And it is definitely, of all the implementation, Mercury is 100% the most accurate of all the spacecraft that they have. That's why I really like Mercury. I don't know, it's just got this old-timey submarine feel that I also really dig. But as we can see, that we're equalizing. And again, that plus 5 psi for structural integrity right down to splashdown and recovery when that hatch opens. So this is a good comprehensive tutorial for the Mercury spacecraft, I would say. I haven't covered emergency situations, but honestly, those are just fun to figure out yourself, right? I don't want to spoil all the fun. There are some things that you should just learn on your own, and emergencies are one of them. They're really fun. I was able to survive by failing every single system, remarkably somehow. I fired the retros at just the right time with no control, and I was somehow able to survive. So it's kind of crazy what you can do in emergency situations, and I recommend just trying them out yourself. And as we could see, the last things to do after impact, ASCS AC off and photo lights off. That's the last thing we have to do. And we'll close out the Mercury Atlas tutorial. we go. ASCS off. And look at that. We get the excess water. It's completely normal. You can act. And now photo lights off. And we can see the rescue lights processing. If we wanted, we can deploy the rescue aids manually. And there it is. Yes, I know, the Mercury has these buoys. You're probably not used to seeing them, but the rescue aids, for whatever reason, never deploy. So you can manually do that. They'll come out for you. Yeah, the campaign's great. Definitely, definitely. If Old Man Rebels on the stream, definitely don't spoil the campaign for Mercury. Is single-handedly the best campaign in all of reentry. So yeah. Thanks for watching, and I suppose I may do a Gemini stream. I don't know. I kind of want to stream for the rest of the hour and a half I have left. I'll tell you what. You know what we're going to do? I know exactly what we're going to do. We are going to... let's do a space shuttle stream. Huh? Hour and a half space shuttle stream? What do you guys think? Let's do that. I'm going to make a new stream. I'll be back.